Lecture 10, Consensus and Agreement Algorithms. Preface. Recap of previous lecture. In previous lecture, we have discussed about mutual exclusion algorithms for distributed computing system, such as non-token based algorithms, quorum based algorithms, and token based algorithms. Content of this lecture. In this lecture, we will discuss about consensus and agreement algorithms. This lecture first covers different aspects of consensus problem and then gives an overview of what forms the consensus are solvable under different failure models and different assumptions on synchrony and asynchrony. Also, it covers the agreement in the category of synchronous message passing system with failures and asynchronous message passing system with failures. Introduction. Agreement among the processes in a distributed system is a fundamental requirement for a wide range of applications. Many forms of coordination require the processes to exchange information, to negotiate with one another, and eventually reach a common understanding or an agreement before taking an application specific actions. A classical example is the commit decision in the database system, wherein the process collectively decide whether to commit or abort a transaction that they participate in. In this lecture, we will study the feasibility of designing algorithms to reach agreement under various system models and failure models, and where possible examine some of the representative algorithms to reach an agreement. Now we are going to see some of the fault models. So let us classify the faults. So based on the component that failed, the components which are basically failing in the distributed systems are classified as either the program or a process or a processor or a machine or a link or a storage. So they are prone to the failures, and we assume that in this discussion that one of these components, if it is failing, how the algorithms are basically going to lead to a consensus or agreement which is required to run the applications. So based on the behavior of faulty component, so the fault models, different fault models will be classified as follows. So the crash fault, there we assume that the system just halts after the problem. Fail stop will crash with some additional conditions. Crash means that it will halt. So omission means it will fail to perform some of the step, that means some of the step it will omit. Byzantine fault, behaves arbitrarily, is the most general fault model. Timing, it violates the timing constraints. These are the different faulty components, and they are basically used up to model the failure models. Now classification of tolerance. Type of tolerance, masking, the system always behaves as per the specification in the presence of faults, that means faults are masked. Non-masking, that system may violate specification in the presence of faults, should at least behave in a well defined manner. Fault tolerant system should specify the class of faults tolerated, what tolerance is given from each class. So these are basically some of the requirements. Now as far as different models are concerned, different assumptions which we are going to use in this particular algorithm design, the assumptions are, we have to assume some failure models. So we have to see what are the different failure models possible. Then we have to make an assumption about synchronous and asynchronous type of communication. Then another assumption we have to make about is network connectivity, sender identification, channel reliability, authenticated versus non-authenticated message, and agreement values. These are the different assumptions which we have to make in the algorithms. We are going to discuss one by one in the next coming slides. So before that, let us see the problems of an agreement. In this particular figure which is shown over here, G1 is basically, this particular problem is about Byzantine journal problem. That is why it is basically G, it is represented as G. So here there are 4 journals and they are leading the troops, and that is why they are the group 1, group 2, group 3 and group 4 different journals. They are located in the Byzantine city, and this particular hill is located in Istanbul nowadays. So at 4 different sites where they will not be able to see each other, and located on the hill, these 4 different Byzantine generals, they have to take the decision either to attack or not to attack, and if they take the decision simultaneously, then they are going to win. If they are not going to take decision simultaneously, then basically they are going to lose. Now some of these particular Byzantine generals are the traitors, and they will communicate whether to attack or not to attack. They have to communicate with the help of message. So here the message are nothing but they are communicated through the messengers, and the messengers or the messages are lost means if these messengers are caught by the army camp. So here this G1, G2, G3, G4, they are Byzantine generals, and they are basically representing their troops at 4 different locations, and these communication links are nothing but they are the messengers. They are able to, they will be sending or they will be communicating with these different journals, and once they are communicated securely, then they have to follow the action whether to attack or not to attack. So here you can see that there are some journals which are traitors also. So depending upon how many journals are traitor, they have to take the decisions. 0 and 1. 0 means no attack and 1 means attack. So let us assume that, so after the set of message exchanges, G4 will receive the messages 0, then 1 and 1, and G3 will receive the messages from the other journals as 1, then 0 and 0, and G2 will receive the messages as 1, then 0 and 0, and G1 will receive the messages as 1, then 0 and then 0. Now can you just see that the messages which they receive, if it is coded in some form, that means it is very difficult to take this particular decision. Why? Because so here it is 100, here it is 100. So you can see that G1, G2 and G3, they have reached to the same values, but as far as G4 is concerned, G4 has a different value. So if let us say it is interpreted as G1, G2, G3 will have the same value, and the majority of it is zeros, that is not to be attacked. As far as G4 is concerned, if we go by this, then it will have 1, and let us say that it is having a decision to attack. So basically here we can conclude that this is basically a traitor, and other non-traitor, that is these journals, they basically lead to a common value, and that is not to attack. So this basically values are arrived at after several message rounds. So still this particular problem is unsolved. Why? Because here G1, G2, G3, they have reached to a common value and G4 is not. So everyone is not agreeing on a common value. So most of the applications, they have to basically depend upon how the agreement is to be arrived at, agreement of same value or agreement of set of values. So these are the problems, and this app has a wide applications. and we are going to see how this particular agreement problem is going to be solved using algorithms, and in what are the models and what are the system models, failure models, where we are going to solve them. So we are going to see these assumptions one by one. A failure model. A failure model specifies the manner in which the component of a system may fail. There exists a rich class of well-studied failure models. The various failure models are fail stop, crash, receive omission, send omission, journal omission, and Byzantine or malicious failures. Now here in failure models among n processes in the system, so we represent it using n small n, and we can also assume that there are at most f different processes can be faulty. So a faulty process can behave in any manner allowed by the failure model, which basically is to be assumed in the particular problem setting. The types of failure models. So the first type is called fail stop. In this model, a properly functioning process may fail by stopping the execution from some instance thenceforth. Additionally, other processes can learn that the process has failed. This is called fail stop. Crash failure model. In this model, a properly functioning process may fail by stopping to function from any instance thenceforth. Unlike the fail stop model, other processes do not learn of this crash. Third one is receive omission failure model. A properly functioning process may fail by intermittently receiving only some of the messages sent to it or by crashing. Send omission. A properly functioning process may fail by intermittently sending only some of the messages it is supposed to send or by crashing. Journal omission. A properly functioning process may fail by exhibiting either or both of send omission and receive omission failures. Byzantine or malicious. In this model, a process may exhibit any arbitrary behavior and no authentication techniques are applicable to verify any claims made. Now the next assumptions in these algorithms are called about the synchronous oblique asynchronous computations. Synchronous computation, a process runs in a lockstep manner. That is, a process receives a message sent to it earlier, performs the computation using those message and send the message to other process. So this is basically lockstep which the process runs in this particular discrete sequence. So steps of synchronous computation is called a round. Asynchronous computation does not proceed in this strict locksteps manner. The process can send receive messages and perform the computation at any point of time. There is no bound in these delays of the messages which is assumed in asynchronous communication. Third type of assumption is called about network connectivity. System has full logical connectivity, that is, the processes can communicate with any other process by direct message passing. Fourth assumption is about sender identification. A process that receives a message always knows the identity of the sender. Fifth, channel reliability. The channels are reliable and only processes may fail. This is very important assumptions. So the failure about processes we are going to, or processors we are assuming under different failure models. So this will simplify our study about different algorithms in this setting. Authenticated versus non-authenticated messages. In this part of the discussion, we will be dealing only with the unauthenticated messages. With unauthenticated message, when a faulty process relays a message to other processes, it can forge the message and claim that it was received from another process, and it can also tamper with the content of the received message before relaying it. Using authentication via the techniques such as digital signature, it is easy to solve the agreement problem, because if some of the process forges a message or tampers with the content of the received message before relaying it, the recipient can detect the forgery or the tampering. So we are going to use only the unauthenticated messages as per the algorithms are concerned. Agreement variable. The agreement variable may be a boolean or a multi-valued and need not be an integer. When studying some more complex algorithm, we will assume it as boolean variable. This simplifying assumptions does not affect the result of other data type, but helps in abstraction while presenting the more details of the insight of the algorithm. Performance aspects of the agreement protocol. Few performance matrices for the agreement protocols are as follows. First is the time, that is number of rounds needed to reach an agreement. Message traffic, that is the number of messages exchanged to reach an agreement. Then storage overhead, amount of information that needs to stored at the processor during the execution of the protocol. Problem specifications. So the problem specification under this agreement and consensus algorithms are as follows. The first one is Byzantine agreement problem. Here the single source has the initial value. So it has three conditions. The agreement, that is all non-faulty processes must agree on the same value. Validity, if the source is non-faulty, then agreed upon value by all non-faulty processes must be the same as the initial value of the source. Termination, each non-faulty process must eventually decide on a value. Consensus problem, all processes have an initial value. Agreement, all non-faulty processes must agree on the same, that is the single value. Validity, if all non-faulty processes have the same initial value, then agreed upon value by all non-faulty process must be that same value. Termination, each non-faulty process must eventually decide on a value. So maybe that you have seen the difference. If you have not noticed, then again I am underlining it. In Byzantine agreement, only one source has the initial value. In consensus problem, all the processes, not only single but all the processes have the initial values, and in both of the cases they have to decide on a particular value. In both the cases they have to decide on a particular value. So only the problem setting is different. Here in consensus all the processes have their initial values, where in Byzantine agreement only the single source has the initial value. Third type of problem is called interactive consistency problem. Here all the processes have the initial values. So agreement, all non-faulty process must agree on the same array of values. This you have to notice that this is the difference, where the earlier two methods they have to agree on a single value. Here they are agreeing on a set of values, that is an array of values. Validity, if a process I is non-faulty and its initial value is Vi, then all non-faulty processes agree on Vi as ith element of the array. If Pj, process j, is faulty, then the non-faulty processors can agree on any value for Aj. Termination, each non-faulty process must eventually decide on an array. So the array of a particular element shows that this value, if they agree, if it is a non-faulty, then they have to agree on that initial value, and if it is a faulty, then they have to agree on any value. So this particular array will be built for n different processes, 1 and so on up to n, and so at the termination all non-faulty process must decide on this particular array. This array will be exchanged at all the non-faulty. So this is called interactive consistency problem. Among three problems there is an equivalence. So three problems defined above are equivalent in the sense that a solution to one of them can be used as a solution to the other two problems. This equivalence can be shown using a reduction of each problem to the other two problems. For example, if a problem A is reduced to a problem B, then the solution to a problem B can be used to solve a problem A in conjunction with the reduction. Formally, the difference between the agreement and the consensus is that in agreement problem a single process has the initial value, like in a Byzantine agreement, whereas in consensus problem all the processes have the initial values. So So however, and they are equivalent, that means if you know how to solve a Byzantine agreement problem, then basically the solution of that Byzantine agreement problem can be used to solve the consensus problem and interactive consistency problem. So overview of the results. The following table gives an overview of the results and the lower bound on solving the consensus problem under different assumptions. It is worth understanding the relation between the consensus problem and the problem of attaining common knowledge of the agreement value. For the no failure case, consensus is attainable, that we will see in that the next table. Further, in the synchronous system, common knowledge of the consensus value is also attainable, whereas in the asynchronous case, concurrent common knowledge of the consensus is attainable in no fault situation, that we can see in this figure. So if the failure model is no failure, and in the synchronous model the agreement is attainable and common knowledge is also attainable. If it is asynchronous message passing and a shared memory system, then agreement is attainable and also the concurrent common knowledge is attainable. But if the failure model is a crash fault or a crash failure, then agreement is attainable in the synchronous system, and f, the number of faulty processor, is assumed to be less than the total number of processes, and it will be resolved, that is agreement can be attainable in the f plus 1 of a lower bound number of rounds. That means minimum f plus 1 round is required to basically achieve the agreement. However, in asynchronous model, even for the crash fault or a crash failure model, agreement is not attainable at all. If the fault model is Byzantine, then the agreement is attainable in the synchronous system, where the faulty number of processor is less than or equal to the floor of n minus 1 divided by 3, and this particular agreement is achieved in the lower bound of f plus 1 number of round, where f is the faulty number of nodes. However, in asynchronous model, the agreement under Byzantine failure is also not attainable, because if it is not attainable in the crash fault, then obviously it will not be attainable in the Byzantine faults. So consensus is not solvable in asynchronous system, even if one processor can fail by the crashing. So the next figure further shows how asynchronous message passing system and a shared memory system deal with trying to solve the consensus problem. Now, since you know that impossibility of the consensus problem under asynchronous system, so what we can do is basically we can solve a variance of this consensus problem in this model, that is in asynchronous system, and that is shown here. So under message passing system, a variant of the consensus problem is called K-set consensus, epsilon consensus, renaming, and reliable broadcast, that we will see in the next few slides the more detail about them. Now the weaker consensus problem in asynchronous system, we are just trying to understand what these problems are. Terminating reliable broadcast, it states that a correct process always gets a message even if the sender crashes while sending it. K-set consensus, it is solvable as long as the number of crash failures f is less than the parameter k. The parameter k indicates that non-faulty processes agree on a different values as long as the size of the set of values agreed upon is bounded by k, that is called K-set consensus. Approximate agreement, like K-set consensus, approximate agreement also assume the consensus value is from multi-valued domain. However, rather than restricting the set of consensus values to a set of size k, it says that epsilon approximate agreement requires that the agreed upon value by the non-faulty processor is within epsilon of each other. Renaming problem, it requires the processes to agree on necessarily a distinct value. A reliable broadcast, a weaker version of a reliable terminating broadcast, namely the reliable broadcast in which the termination condition is dropped, is solvable under the crash fault. To circumvent the impossibility results, the weaker variants are defined in the next table. So, reliable broadcast failure model, if it is crash fault, it requires uh, the condition n is greater than f. Similarly, k set consensus, then basically the value of k should be more than f and should be bound less than n. Epsilon agreement crash failures, this particular model is working, n is should be greater than equal to 5f plus 1. Renaming up to f fail stop processes it can sustain, and n should be greater than 2f plus 1, and for the crash fault f is less than n minus 1. Agreement in synchronous message passing systems with failures. Consensus algorithm for crash failures, message passing synchronous system. So, algorithm given in the next slide gives a consensus algorithm for n processes where up to f processes where f is less than n may fail in a fail stop failure model. Here the consensus variable x is integer valued. Each process has initial value xi. If up to f failures are to be tolerated, then algorithm has f plus 1 rounds. In each round a process I sends the value of its variable xi to all other processes if that value has not been sent before. So, of all the values received within that round and its own value xi at that start of the round, the process takes minimum and updates xi after f plus 1 rounds. The local value xi is guaranteed to be the consensus value. Let us understand it using this particular algorithm that is explained earlier. So, we can understand that if let us say that we have 3 different processors and let us say one is faulty. So, f is equal to 1 here in this case. So, the agreement requires f plus 1 that is equal to 2 rounds. If it is faulty, let us say it will send 0 to one process and 1 to another process I, j and k. Now, on receiving 1, on receiving 0 it will broadcast 0 over here, and this particular process on receiving 1 it will broadcast 1 over here. So, this will complete one round. In this one round, and this particular process on receiving 1 it will send 1 over here, and this on receiving 0 it will send 0 over here. So, you can see that here it will receive 0 and 1, and this will receive 0 and 1, this will also receive 0 and 1, and the minimum if you take this will be having 0, 0 and 0. So, if let us say that it sends 1 back to him, if it receives 1, then let us say it receives 1 in that case. So, it is 0, 0 and 1. So, this is round number 1. So, similarly, if you take another round of these particular messages, and if this is having value 1, this is having value 0, this is having value 0, if they exchange with each other and take the minimum, then all of them will have the value 0 and they will reach to a consensus after 2 rounds. So, the complexity of this particular algorithm is it requires f plus 1 rounds where f is less than n, and the number of messages is order n square in each round, and each message has one integer, hence the total number of messages is f plus 1 into n square. F plus 1 is the total number of rounds, and in each round n square messages are required. Now the next most important algorithm in today's lecture is given here, that is consensus algorithm for Byzantine failures. This algorithm is given by Leslie Lampard. This is called Shostak-Pease-Lampard algorithm. This is for Byzantine failures. So it is assuming a synchronous system and the failure model is Byzantine, and we are going to see this particular algorithm. So in this algorithm, the model which is assumed is saying that there are total n processes and f can be the faulty. The communication is reliable and it is fully connected topology. Receiver always knows the identity of the sender, and here the fault model is assumed as very general fault model, that is Byzantine. And the synchronous system, in each round a process receives a message, performs computation and sends. So synchronous computation model is assumed here. So the solution of the Byzantine agreement is first defined and solved by Leslie Lampard. So Lampard Shostak-Pease algorithm it is. So Pease showed that fully connected network, it is impossible to reach an agreement if the number of faulty processor f exceeds n minus 1 divided by 3. That is, f should always be less than or equal to n minus 1 divided by 3. So let us take this particular example, whether this example shows that the condition where f is less than n minus 1 by 3 is violated over here. That means if f is equal to 1 and n is equal to 3, this particular assumption is violated. That means n minus 1 by 3 is not 1 in that case, but we are assuming 1. So obviously, as per the previous condition, agreement, Byzantine agreement is not possible, and we can see in this particular example. Here P0 is faulty, is non-faulty, and here P0 is faulty. So that means P0 is the source. If the source is faulty here in this case, and source is non-faulty in the other case. So source is non-faulty, but some other process is faulty. Let us say that P2 is faulty. So P1 will send, because it is non-faulty, same values to P1 and P2, and as far as the P2 is concerned, it will send a different value because it is a faulty. So this agreement will not be reached here in this particular example. So same example, we can see that agreement is not possible. Now agreement is possible when f is equal to 1 and the total number of processes is 4. So agreement, we can see how it is possible. We can see about the commander PC. So this is the source. It will send the message 0. Since it is faulty, so it will send 0 to PD, 0 to PB, but 1 to PA in the first round. So PA, after receiving this 1, it will send 1 to both the neighbors. Similarly PB, after receiving 0, it will send 0. Why? Because it is non-faulty. Similarly PD will send after receiving 0, 0 at both the ends. So if you take these values which will be received here, it is 1 and basically it is 0, and this is also 0. So the majority is basically 0 here in this case. Here also, if you see the values 1, 0 and 0, so the majority is 0, and here also majority is 0. So in this particular case, even if the source is faulty, so it will reach an agreement, and that value will be agreed upon value, or agreement variable will be equal to 0. Similarly here in this example also, let us assume that that some other node is faulty in that case. So for example, if it receives 0, and this receives, yeah, this is faulty in this case. Why? Because after receiving 0, it will send 1 and 1 in both the cases. So we will see that in the same manner this also will reach to an agreement. And so as far as Lampert-Sostek peace condition is concerned, if the condition is satisfied with the number of faulty processors, then the agreement is possible. So the algorithm is called as a Lampert-Sostek peace algorithm. This algorithm, also known as oral message algorithm, OMF. F is the number of faulty processors. So the number of processors n should be greater than or equal to 3f plus 1. The algorithm is recursive, and the base of the recursion, that is OM0, says that the source process sends its values to each other process. Now each process uses its value it receives from the source. If no value is received, the default 0 is assumed. Now recursion, recurse procedures of this algorithm OMF. F is greater than 0, then the first step says that source process sends its values to each other process. Now for each I, let Vi be the value the process I receives from the source. Now default 0 if the value is not received. Process I acts as the new source and initiate algorithm OM f-1, where it sends the value Vi to each of n-2 process. Now finally, after this particular for loop is over in step number 2, then fourth step says that for each I and j not I, which is not equal, j is not equal to I, j is not equal to, let Vi be the process I received from the process j. In step number 3, process I uses the values using the majority function v1 to vn-1. The function majority computes the majority value if exists, otherwise it uses the default value as 0. So this majority function is application dependent, but so this basically will be the algorithm which is applied under the Byzantine fault model and under the synchronous communication system model. So as we have seen that f is equal to 1 and n is equal to 4, the same algorithm we have applied in the previous slide. Now let us see how many messages, how many rounds will be there. Now as you know that it will require how many 2 rounds will be required. So in each round the total number of messages in each round will be 3. For example, a source will send to its neighbors. Similarly, in the second round, now each of these will send to its corresponding neighbors. So basically 6 messages in second round and 3 messages in the first round. So total 9 messages will be required here, and the total number of rounds will be the 2, that is f plus 1, that is equal to 2, and the messages will be as equal to n minus 1 plus n minus 1 multiplied by n minus 2. That is n minus 1 means 4 minus 1 minus 1, that is 3 plus 6, that is 9. Total 9 messages will be there. So if we generalize this particular total number of messages, now if f is equal to 2, then n is equal to 3f plus 1, that is equal to 7. So 7 is required, and for the number of faulty processes are 2. So this particular model, or in this particular case, Byzantine agreement is possible. And how many number of rounds it is going to take? F plus 1, that is 2 plus 1, that is 3 rounds. So here just see that in this particular picture 3 rounds are shown, and let us understand that in the first round the source will send the message to all other neighbors except itself. So it will send to 2, 3, 4, 5, 6. Now every node will do this way. That means we have to see how the node 4 is now doing it. Node 4, after receiving this V1, it will send to its neighbors. So its neighbors other than the previously defined neighbors or previously received messages are not to be included in that. So it will send the message to 2, 3, 5, 6, 7. Now among them 2 will in turn will send to its neighbors other than from where it has earlier previously received the message, that is 3, 5, 6. So third round, when every node is complete, the algorithm will finish, and let us analyze how many number of messages will be communicated over here. So the total number of rounds, as you have seen, is equal to 3, and the messages required will be equal to n minus 1 plus n minus 1 times n minus 2 plus n minus 1 times n minus 2 times n minus 3. And if you see, because this is round number 1, this is round number 2, and this is round number 3, different messages. So total number of messages, you have to sum total number of messages which are basically communicated in each round. So if you sum them, it comes out to be 156 different messages. So we have seen two examples where f is equal to 1 and f is equal to 2. Now we are going to see a more complicated example where f is equal to 3. When f is equal to 3, the total number of nodes will be 10. 3f plus 1, that is equal to the 10, and the number of rounds will be f plus 1, that is 3 plus 1, that is 4. So just see that in this particular figure number of rounds are 4, and as we have seen in the previous example that up to round 3 we have seen, similarly the round 4 will also continue, that every node will send the message to its basically neighbors and will not send to the other neighbors who have previously sent the message to that particular node. So this example, as written over here, only one branch of the tree is shown for the simplicity. What you can do is you can explore the complete example at your end. Similarly, if we see the message complexity, number of rounds, as I told you, is equal to f plus 1, that is 3 plus 1, 4, and the messages, total number of messages will be n minus 1 plus n minus 1 times n minus 2 plus n minus 1 times n minus 2 times n minus 3, 1, 2, and 3. So, and the fourth round will take n minus 1, n minus 2, n minus 3, and n minus 4. So total number of messages, if you count, they comes out to be 3609 messages in this particular example. So we can generalize these particular formula, and so number of rounds is very simple calculation, that is f plus 1 rounds, but as far as the messages are concerned, it goes to an exponential, that is why it is called exponential algorithm, because exponential of the order messages are required here in this particular example. In this particular exponential amount of space and messages are required. Now agreement in asynchronous message passing system with failures, impossibility result for consensus problem, Fisher, Lynch and Patterson, FLP, impossibility result it is called. So in 1985 this particular impossibility result is called FLP impossibility result. Fisher showed that the fundamental result on the impossibility of reaching an agreement in asynchronous system, it is stated that it is impossible to reach consensus in an asynchronous message passing system, even if a single process has a crash failure. This result, popularly known as FLP, impossibility result, has a significant impact in the field of designing distributed algorithm in a failure susceptible systems. So that is why a weaker versions of consensus problem in asynchronous system, asynchronous model of communication is basically devised, and these are called terminating reliable broadcast, K set consensus, epsilon approximate agreement, renaming problem, and reliable broadcast. Terminating reliable broadcast problem. A correct process always gets a message even if the sender crashes while sending it. So validity, if the sender of the broadcast message M is non-faulty, then all the correct processes eventually deliver M. Next problem is called reliable broadcast problem. Reliable broadcast problem is without terminating condition. RTB requires that eventual delivery of the message even if the sender fails before sending it. In this case, the null message needs to be sent. In reliable broadcast, this condition is not there. In RTB requires recognition of the failure even if no message is sent. So is solvable under the crash failure of the order n square. Now applications of this agreement algorithm are many. So some of them are listed over here. As first application is called as a fault tolerant clock synchronization. Distributed systems require physical clock to be synchronized. So agreement protocol may help them to reach a common clock value. Atomic commit in distributed database system. So distributed databases sites must agree on whether to commit or to abort. The transaction agreement protocol may help to reach a consensus. Conclusion: consensus problems are fundamental aspects of distributed computing because they require inherently distributed processes to reach an agreement or a consensus, and which is essential in many of the applications. So this lecture covers different forms of consensus problem, then gives an overview of what forms the consensus are solvable under different models, failure models, and different computation models. Then we have covered the agreement in the following categories: synchronous message passing system with failures, used the fault model, fail stop, and Byzantine models. We have seen two different algorithms. Asynchronous message passing system with failures, we have shown the FLP impossibility condition in this problem setting. It is impossible to reach the consensus in this model. Hence several weaker versions of the consensus problem, that is terminating reliable broadcast are considered. In upcoming lecture we will discuss about checkpointing, and thank you.